take a picture of this slide, please. So particularly for the people who took the course a long time ago, and you'll need these formulas probably. Again, if you cannot memorize, take a picture of the slide. And also on this slide, you'll have all the basic integration formulas I want you to memorize. I wanted you to take a picture of the slide, I think last week, right? We now officially start Calculus 2. Last week we did some review on integration, in particular the substitution rule. We also did a little bit of new thing, L'Hopital's rule. But the main thing in Calculus 2 is integration calculus, integrals. In this week we are going to learn some techniques, including the integration by parts formula and some other things. And then next week we'll do some applications, simple applications. And then after simple applications, we go back to learn more techniques, integration techniques, I mean. After that, we learn more applications. After that, we'll do some other stuff like differential equations, series, and so on. Okay. The first new thing is integration by parts. Integration by parts. Now let's recall I told you before, integration and differentiation are kind of reverse operations. Integration by parts is equivalent to the product rule in differentiation calculus. The formula on the screen is called the integration by parts formula. Very shortly we are going to practice many questions using the formula. But I want you to know the formula is equivalent to the product rule in differentiation calculus. We do not talk about the proof at this time. If we have time at the end of the class, I'm going to talk about why the formula is true. So basically the proof of the formula. These two forms are equivalent. In most cases, we use the second form. We use the form in here. The integration of u dv. It's kind of a symbolic formula. It's equal to u times v minus the integration of v du. You're going to see how powerful the formula is for handling many integrals. Take a picture of the basic formula. We're going to practice many questions using that formula today. Okay. In particular, you look at the remark. When to use the integration by parts. So take a picture. I'm going to make a comment on the remark very shortly. The first question I want to go over is question 1 on part 1. I told you to download handout number 2 to get the file. I'm going to comment this part. The formula for integration by parts can be used to find the integrals in the form of that. So basically the integrand, by integrand I mean the function inside the integral. The integrand is a product of two functions, having the condition that the derivative of one function is simpler, the derivative of one factor is simpler, and the antiderivative of the other factor is not too complicated. It's not more complicated. Okay, I will show you what I mean. The derivative of x is equal to 1. The constant function 1 is simpler than the linear function or power function of x, right? The derivative of one function is simpler. Anybody want to tell me what is the antiderivative of cos of x? Antiderivative of cos of x? Antiderivative of cos of x is equal to, we think which function has the derivative of cos of x. Antiderivative of cos of x is sine of x, right? I hope it makes sense. Sine of x is not more complicated than cos of x. Using our common sense, sine of x, which is the antiderivative of the other factor, which sine of x is not more complicated than cos of x, right? Using our common sense to understand what I mean by simpler and not more complicated. The derivative of x is equal to 1, which is simpler than x. Antiderivative of cos of x is sine of x, which is not more complicated, right? In this case, we are going to use the by parts formula. We can use the by parts formula. At least you can think about using the by parts formula to integrate the function. The key is how to choose u and dv. I will show you how to choose u and dv. The formula is here. I'll just move the integral to here. Choose u to be one of the two factors for which the derivative is simpler. Okay. So we let u be x. So because the derivative of x is simpler, the derivative of u is equal to 1. So which is simpler than x. And the dv is the differential of v. dv is the differential of v. Sorry, I should not have written then in here. You just remember to choose the other function. Now let's recall the integrand is the product of two functions. We choose u to be x. For all the rest inside of the integral, we set it to be dv. We let all the rest be dv. So by that we mean we set dv to be cos of x and then dx. Here is the differential of v. We are looking for a function v. We are looking for one particular function v, having the condition that the differential of v is cos of x times dx. Essentially, v is the antiderivative of cos of x. Okay. Now let's go back to the formula. We have chosen u in here. We have chosen dv in here. The integral in the form of u dv, which is the given integral, is equal to u times v. We need to get u, we need to get v, right? And then we compute the right hand side of the integral in the formula. To get the right hand side, in order to compute the right hand side, we have to get what we need for the right hand side. Okay. And then we compute du. On the right hand side we have du, right? Du is the same as before. It's the differential of u. The differential of u. You take the derivative of the function and then you multiply the derivative by dx. You have the differential of u. Okay. So du is equal to the derivative of x is equal to 1, right? Is equal to dx. So basically 1 times dx. That's how we get du. And then I told you how to get v earlier. I will repeat. V, we are looking for a function v having the property that the differential of v is equal to cos of x times dx. It's here. By that I mean v is actually an antiderivative of cos of x. We just need one particular antiderivative. Antiderivative of cos of x is sine of x. To get antiderivative, you think which function has the derivative of cos of x, right? Now we are ready to use the given formula. The given integral now, I will copy it down. The given integral now, if we set u to be x, we set dv to be cos of x and dx. For this function, yeah, probably I'm going to show you how to use the formula. Okay. So the integral is in the form of u times dv, right? So that's u. This part is dv. That's in the form of u dv. Now the by parts formula, and by the way, you can call it by parts formula. People just call it by parts formula. The full name is integration by parts formula. We just call it by parts formula. Okay. Using the by parts formula, it's uv minus the integral of v du. Remember that formula. Okay. I'm going to copy the formula here. It's u times v minus the integral of v du. If the condition is true, by the condition I mean the derivative of one factor is simpler, the antiderivative of the other function is not more complicated. If that's the case, in the new integral on the right hand side, in many cases, is simpler than the original integral. I'm going to show you what I mean. Okay. Now let's plug in the functions. We plug in the functions. U is x. On the right hand side, you have u times v. You have two functions of x. Everything in the formula are functions of x. Okay. U times v minus v du. Now let's look at v du. You are going to see the function, the integral is simpler. V is sine of x. Du is just dx. So do you see the integral is easier to compute? Now all we need is to compute the indefinite integral of sine of x. Sorry, I forgot x in here, guys. We are almost ready to have the final answer. So the final answer is x times sine of x and then minus. So here we are looking for antiderivative of sine of x. So don't be confused with the derivative. Antiderivative of sine of x, we are looking for which function has the derivative of sine of x. Anybody want to write something down? I haven't asked you a question for a long time. What is the antiderivative of sine of x? Antiderivative of sine of x is negative cos of x. Okay. And then we combine with the negative sign here, we turn the sign to plus. Okay. Cos of x. After getting rid of all the integration notations, do not forget to plus C. Okay. That is the final answer. Now let me summarize a little bit, okay? So basically I want to repeat something I told you earlier. That's a simple question showing in which case we need to use the by parts formula. Again, the by parts formula, the full name is integration by parts formula. If the integrand is the product of two functions, and the derivative of one factor is simpler, the antiderivative of the other function is not more complicated. In this case, we use the by parts formula. Choose u to be the function for which the derivative is simpler. Choose all the rest to be dv. And then you compute du and get v. I want to mention you just need one particular antiderivative of cos of x in here. Okay. And then you follow the formula. In many cases, the integral on the right hand side, that integral is simpler to evaluate. And then you evaluate, you have the answer. Simple enough. Any questions? Any questions? If you don't have any questions, we move on. Okay. For all the questions are essentially the same. So just the integral is getting more and more complicated. We just talk about more cases. The basic idea is here. Okay. If you don't have any questions, we'll move on to question. Actually, all the questions like 1, 2, 3, 4 are similar. Can I jump to question 4? I'm going to jump to question 4. Okay. If you know how to do question 4, then you know how to do question 2. I will jump to question 4. I will go over at least one other question before you try. In many cases, the key is how to choose u, and dv. Okay. Anybody want to write down how to choose u? Choose the integrand is the product of two factors. Choose u so that the derivative of one factor is simpler. So please, anybody want to write down how to choose u? Please. Yeah, choose u to be x squared. So we let u be x squared. The derivative of u is 2x. The derivative of x squared is 2x using the power rule. Okay. So the derivative is simpler. And the other function, together with dx, we use dv to denote that. So basically, the dv is the notation for differential. Okay. So dv is equal to cos of 2x and then times dx. That's how we set up. The next thing you do is to compute du and v. du should be simple, right? So du, you just differentiate u and then times dx. The derivative of 2x is the derivative of x squared is 2x, and then times dx. You have du. We did that over and over again when we talk about the substitution. V is a little bit weird. So later on, I will tell you how to memorize some stuff. But at this point, V is supposed to be a particular antiderivative of cos of 2x. Anybody want to write something down telling me what is a particular antiderivative of cos of 2x? you think which function has the derivative of cos of 2x. So do not write too quickly. There's a little trick in here. No, it's not quite right. I think you kind of differentiated. Now we are looking for antiderivative. We are looking for which function has the derivative of cos of 2x. I'm going to write something here. We are looking for a function having the property that the derivative is cos of 2x. You got it right. It's half of sine of 2x. Okay. So the question mark here is half of sine of 2x. You differentiate that. You use the Chen rule. You have to think about the Chen rule. Okay. You differentiate that. You have half of the derivative of sine of u is equal to cos of u. I said u. We imagine u is 2x. Okay. It's cos of 2x, and then followed by the derivative of u, so which is 2. Right. So the derivative of that function is what? It's cos of 2x. So which means this function is the antiderivative. This function is a antiderivative. We just need one particular antiderivative. Okay. So here we need one particular antiderivative, which is half of sine of 2x. That's basically the setup. Okay, on the right hand side of the screen, I will tell you something in general. Okay, in general, if dv is equal to, so let's say maybe in general, yeah, probably I could tell you something to memorize. Okay, so now let's say if dv is equal to, so we just said, now let's say cos of, now let's say kx, k can be 2, can be 3, can be 5, can be anything. Okay, dx, what would be v? Can anybody guess? So just to try to generalize the pattern we just did. I'm telling you something to memorize so that it's easier for you in the future. We are thinking which function has the derivative of cos of kx. It would be some number times sine of kx, right? So what's the number before? It would be 1 over k. Does that make sense? I should have mentioned the k is not equal to 0, but now let's assume that. That's one case I want you to remember at least. If you know what's going on, you don't need to remember. But that's, can I say that case 1? I will give you a few other cases. Okay. So now let's say if dv is equal to, dv, that's my v. If dv is equal to, now let's say sine of kx. So dx. Anybody want to tell me how to get v, how to get a particular antiderivative of sine of kx? So tell me v, please. Tell me v, please. Write something in the chat box, please. We are thinking which function has the derivative of sine of kx. It would be 1 over k cos of kx. Is that right? That's not right. There should be a negative sign. Okay. We are looking for antiderivative of sine of kx. You think which function? Yeah, that's right. I think Karen threw something right. Actually, there's one other case I want you to remember. So that's the second case you are going to see in integrals over and over again. That's why I'm writing this down. The third case I want you to know is if, now let's say the differential of a function v is equal to e to the power of, now let's say kx, and then dx. What would be v? and then v is equal to, so please, can anybody write something down? The function now is e to the power of kx. K is a non-zero number. Now I'm looking for a function v. So basically I'm looking for an antiderivative of e to the power of kx. You think which function has the derivative of e to the power of kx? E to the power of kx. The number before that is 1 over k. You have 3 cases here. You can take a picture or you should write it down properly. So because you are going to see functions in those forms over and over again. So that it's easier. Okay. For this function, I'm going to do Wilmot to see what's going on. Now the given integral. The given integral now is the given integral now is in the form of u dv. For the first few questions, I really want you to copy the formula so that you have something to follow. Using the parts formula, using the integration by parts formula, we have uv, the integral of u dv is equal to u times v minus v du, right? And just continue from here. And then we plug in functions. You have u in here, you have v in here, u times v. You leave the constants before the functions. U times v is equal to half of x squared, and then times sine of x, that's sine of 2x, that's uv, right? And then minus v du, you just plug everything in, minus v du. V is equal to 1/2 of sine of 2x du. Now du is 2x times dx. 2x times dx is du. Okay. I'm going to write dx in here. I leave out the constant of 2. And then, so do not forget there's a x in here. So basically 2 and 2 is cancelled. 2 and 2 is cancelled. You do not have to include that term. No. Well, temporarily, so leave it there. Okay. Anybody want to tell me how to move on? Later on, I'm going to summarize for what form of the integrals you can use the by parts formula. But now, anybody want to tell me how to move on? After using the by parts formula once, we need to evaluate a new integral in something like this. So please, write something down or tell me how can we move on. Please.
Oh, you have to do all that again, but
yeah,
with the sine 2x?
Yeah, that's correct, Chad. We do that all over again. So basically, so do you see you use the by parts formula once, you reduce the power of this power function by 1. And then the form of the integral is kind of similar to that, right? It's kind of similar to that. And then we just use the integration by parts formula again. Okay. Probably I want to leave the complete solution to on one screen so that you can see everything here. Okay, now for the new integral, I'm going to integrate, to compute that integral, to evaluate that integral separately. Okay. For the integral, now let's say x sine of 2x, and then dx. We have to do the whole thing all over again. So now remember, for any one question, so within the question, do not use repeating notations. I'm trying to say do not use the same notation for different things. Okay. Now, this time you still want to choose u and v. You want to use uppercase letters for the new u, for the new v. Okay. We choose u and v again. I believe all of you guys know what's going on in here. Okay. We choose uppercase u to be x, to be one of the two factors. The derivative of that is simpler, right? And now dv, d uppercase to v is equal to what? Is equal to sine of 2x, the other function, times dx. Okay. Now I will give you a chance to practice the following, to practice how to integrate that integral. So please. And probably for this question, I'm going to ask you a question and then you answer question. So d uppercase u is easy, right? du is actually dx. You'll see it's going to work. And the v is a particular antiderivative of sine of 2x. Anybody want to write it down? What's antiderivative of sine of 2x? Yeah, probably Tyler got the final answer right. I'm not 100% sure yet. I don't remember the final answer. I cannot see the final answer at this time. Okay. I think you have been doing it faster than me. Okay, v is negative 1/2 of cos of 2x. Okay. If you have it here, and then we'll move on. Okay. Then the integral of, now let's say x, now let's say sine of x, and then dx. That's your u, so that's your dv. Okay, we're going to use the by parts formula. In the future, you do not have to write the basic formula here, but you do need to keep the formula in mind. We're using the by parts formula as long as you know which one is u, so which one is v. Okay, in this case, you have uv, right? U is x and v is half of cos of 2x. Probably you have a negative sign here. And then minus v du. You have a negative sign here, so the sign here becomes positive, right? So just use the formula. So here you have v du, the integral of v du, I mean. Okay, you leave out 1/2, I think. You leave out 1/2, and then you have du is dx, right? Just copy that. Eventually you have, I think you have now for this part you have to integrate cos of 2x. I told you how to get antiderivative of cos of 2x earlier, right? Antiderivative of cos of 2x is 1/2 of sine of 2x. You combine 1/2 and everything, you have I think you have 1/4 sine of 2x in here. After getting rid of the integration notation, so do not forget to plus c. Okay. That's not the final answer. That's VDU in the first round. That's VDU in here. I believe you know how to get the final answer. You just plug everything here into here. So how about we just get the final answer? Okay. To complete the solution, I'm going to get the final answer. So the final answer to the integral is going to be sorry, I was trying to reuse the functions, but I didn't move everything over. I think 1/2 of that, and then you just subtract that everything here from the new integral. So can I just write a question mark? Yeah, probably. I will give you the final answer. Okay. Subtract a negative thing, you have a plus sign in here. You have plus 1/2 of x cos of 2x, and then minus 1/4 of sine of 2x, and then plus c. I hope that's the final answer, but you got me the idea already. I think you got the idea already. Okay, so that's a complete solution to this question. Illustrated by this question, I'm trying to tell you, in some cases, you need to use the by parts formula more than once before getting the final answer. Actually, for an integral in that form, if you use by parts formula once, then you can reduce the power of that power function by 1. Okay. Any questions? Any questions about question 4? If you don't, I will give you a in-class quiz question, okay? How about we do question number 5 is going to be your in-class quiz. After question 5, I'm going to summarize some forms for you to use. So how about before number... Okay, I think you're ready to do 5. Now look at 5. You can get started if you know how to choose U and dv. If you need some hint, I'm going to get you started to set you up. Again, the integrand is the product of two functions. We have two factors. The derivative of one factor is simpler. I'm going to repeat when to use over and over again. So basically, that's how the by parts formula works. The derivative of one factor is simpler. The derivative of x is 1. 1 is simpler than x. And the antiderivative of the other factor is not more complicated. Actually, antiderivative of e to the power of 3x is a number of times the same function. It's not too complicated, right? It's always easy to handle constant factors. Now for the solution, we want to choose u to be x, and then we want to choose dv to be e to the power of 3x, and then times dx. I will give you a few minutes to get me the complete solution to the question. When you are done, you can write the answer on the screen. I mean, in the chat. It's okay to compare answers. du is simple too. Du, I believe, is dx. I will stop here. Anybody want to tell me v? V, please. Yeah, one third of that is right. It's e to the power of 3x and then times 1/3. Because you have a 3 in here. To differentiate v, you have to use the Chen rule, right? There should be one. Yeah, that's right. Okay, now you move on. I'm going to stop here. You get me the final answer. So this is an in-class quiz. In-class quiz question. I forgot to make up a folder again. I will remember to do that next time. Before class. You keep on trying. I'm not going to give you the rest of the solution. The question is not hard. I believe you are ready to do this. So do not forget in the last step, when you're integrating e to the power of 3x, there should be a 1/3 involved in here. Antiderivative of e to the power of 3x is 1/3 of e to the power of 3x and then plus. I think that's right, Karen. I think that's right. Okay, you can take your time, try to work on the question to get the answer in the chat. Simple enough. Integration is harder than the differentiation. Yeah, that's why we need to develop many more techniques. Okay. For the integration by parts, for the by parts formula, I'm going to summarize some forms of the integrals for which you can use the by parts formula. So basically, we're going to classify the integrals for using different techniques. If you are not done, you can keep on trying, or at the end of the class, you can take a little bit longer time. I will give you longer time. Okay, now concentrate on the new stuff. Okay. I just call it by parts formula, okay? Or integration by parts. Can be used to evaluate integrals of the following forms. I'm going to add the forms. I'm going to add more forms later after we do more questions. But at this point, I want you to remember 3 forms. I think you have seen it. It can be used to do something like x to the power of m, then sine of something kx. M is a whole number. It's a counting number, positive whole number. Okay, k can be any number. Really, k can be any real number. The idea is that you apply the by parts formula once, you reduce the power of the power function by 1. you reduce exponent of that power function by 1. Okay. Do you need me to write down how to choose u and dv? For this form, always choose u to be x to the power of m, and choose dv to be the other function together with dx. Sine of kx and then times dx. Okay. The second form the second form, you can use the by parts formula. The general form is something like this: x to some power, so maybe to the power of m. If you replace sine with cos, it's kind of the same thing, right? For this one, the way to choose u and dv is kind of the same. The third form, I think we have seen the questions earlier, is an integral in the following form: x to some power, to some positive whole number power. I think we can call them natural numbers, to the natural number power, and then times e to the power of kx. We have seen that over and over again. We have seen that a few times already. That's the case. You choose u to be x to the power of m, and then you choose dv to be e to the power of kx, and then dx. Okay. After we, you see, in terms of the integration, these three functions have very similar properties: sine of kx, cos of kx, and also e to the power of kx. These three functions have the very similar properties. After you learn the last chapter, series, you are going to see why these three functions are very similar, actually. Okay. Surprisingly, e to the power of some x, kx, is very similar to the property of sine of kx or cos of kx. After we learn series, you are going to have better understanding why that's the case. Any questions? If you see integrals in one of these three forms, we can use the by parts formula. Okay. Using by parts formula once, you reduce exponent by 1. That's how it works. The next question is a little bit weird. So how about we just... I'm not going to make too many comments. We just start to try. You're going to see what we are going to get. It's kind of interesting here. Actually, you could start with the okay. Now let's choose u and dv. So how about you take a guess how to choose u and dv? So just tell me how to choose u. So take your best guess. How can we choose u? Choose u so that the derivative of the function is simpler. Antiderivative is not too complicated. I think my principle is true in most cases, but it's not quite true in this case. So we just try something to see what we are going to get. In many cases in math, you have to try something, right? How about we just choose u to be e to the power of x, and then we choose dv to be the other function, okay, times dx, cos of x, and then dx. So we'll just see what we are going to get. Now look at the formula sheet for differentiation. The derivative of e to the power of x is e to the power of x, right? So do not forget dx. Dx is part of the differential notation. And then to get v, you need a particular antiderivative of cos of x. I think you have sine of x. You think which function has the derivative of cos? And then we move on to use the by parts formula. I told you in the future you do not, after introducing v, you have to tell me how to choose u and dv here. But in the future you do not have to include u and v in here, as long as you know which one is u, which one is dv. Okay. Using the by parts formula, we compute the u times v. U times v is e to the power of x, then times sine of x, right? And then minus the integral of v du. Integral of v du. V du, you have sine of x is your v, right? Du is e to the power of x, and then times dx. I change the order because in the original integral we have that order. Okay, and also the meaning of this order is better. The notation is less confusing, I mean. After using the by parts formula once, you kind of having the integral at the same difficulty. How about we just move on to see what's going on, okay? So later on you are going to see how the whole thing will work. We just keep on trying. I think if I did the question the first time, I could give up at this time. You end up with a new integral at the same level, okay? But I know the trick. I'm going to tell you the trick very shortly, okay? But we'll move on, okay? We'll move on. For the resulting, for the integral on the right-hand side, I mean for that integral, we'll try to use the by parts formula again, okay? We set uppercase u to be e to the power of x, and we set uppercase dv. Sorry, that's my dv. We set uppercase dv so to be the whole thing of that. So now let's say sine of x, and then dx. So because I knew the trick, actually I will tell you the trick very shortly. There's a little tricky stuff in here. And then you want to use the by parts formula, you have to compute du and v, right? Du is e to the power of x, and then times dx. We have seen that before. The derivative of e to the power of x times dx. And then we need to get v. V is a particular antiderivative of sine of x, which is negative cos of x. Again, the derivative of sine is cos. Antiderivative of sine of x is negative cos of x. You think which function has the derivative of sine, right? Copy and paste don't work well. I will copy the integral. I will copy that integral, okay? Now e to the power of x times sine of x and then dx. We use the by parts formula for this integral using that setup. U times v, I think you have negative e to the power of x cos of x. That's uv. And then minus v du. Minus v du. Minus have a positive, okay? I believe the sign is positive. So what's v du? V du is e to the power of x, and then times cos of x, and then you have dx in here. It's kind of you are going back to the given integral, right? in many cases, if you do something to go back to the given integral, now listen to me. In general, the problem can be solved. Here, I will tell you the trick very shortly. Now let me show you what I mean. Okay, the given integral now is. Can I start a new page? The new integral now is equal to. I'll copy something from here. I don't know why it doesn't copy. E to the power of x sine of x good. Hope I have copied everything. I think I need to change some signs, right? The sign here should be plus, the sign here should be minus. Does that make sense? If you look at here, you had a subtraction in here. You had a subtraction in here, and then you subtract the whole thing from here. The sign here should become plus. The sign here should become minus. I think I got this right. Again, I want to repeat, in many cases, if from the required integral, if you can go back to the original integral, the integral can be evaluated. It's kind of you are going to solve an equation of the integral. Okay. Now let me show you what I mean. Okay. So can I use I to denote the given integral? Now let I be the given integral. No, not that. Right. Now look at the equation on the top. The equation on the top will give you an equation of I, from which you can solve the equation for I. So I is equal to e to the power of x times sine of x plus e to the power of x cos of x minus I, right? So this integral is I. So do you see you have a equation of I? Solve the equation of I, then you can have the answer. Okay. From that you have 2I. I don't know what I was trying to write. I think I was trying to write so. From that you move I on the right hand side to the left hand side. I think you have 2I equals e to the power of x sine of x and plus e to the power of x cos of x. After getting rid of the integration notation, you need to plus c. Okay. So how about we plus c at the end? I is the integral in the question, the integral we want to evaluate. You divide two sides of the equation by 2, so you have I equals the whole thing on the right hand side divided by 2 sine of x, and then plus e to the power of x cos of x. After getting rid of the integration notation in the final answer, do not forget to plus c. That's how it works. Represented by that question. In many cases, actually for many questions, if you can return, if you apply the integration by parts formula, if you can return to the given integral, you can solve the equation for the integral. The given integral can be evaluated. Any questions about this? If you don't have any questions, I'm going to add one more form. The one more form I will squeeze in here. The next form is the integral in the form of the following. Okay, I think the form is e to the power of any number. Now let's say kx, and then the function, it can be sine of, so maybe tx. T is a constant, okay? T is a constant, k is a constant. It's probably not too good to use t as a constant. I'm going to replace t with, how about that? I'm going to use m or n, okay? nx or alternatively sine can be replaced with cos. E to the power of kx, maybe cos of nx. If you have an integral in that form, the integral is essentially the same thing as what we just did. So basically you choose, you apply by parts formula twice, the integral will return to the given integral with some coefficients. Yeah, and then you solve the equation for the integral. So you have four forms for which you can use integration by parts formula. Compute that integral.
Okay.
Right. So the answer, the answer I, solve the equation for I as the answer to the given integral.
Okay.
So that makes sense? Okay.
Yeah.
Okay. Now look at the question on the screen. I believe that's number 7 on the handout. Anybody want to tell me how to choose U? Or write down how to choose U, please. Write down how to choose U, please. X squared will not work. Sorry, I'm trying to trick you. X squared will not work. I know the derivative of x squared is simpler, but the derivative of natural log of x is 1 over x. Later on, I'm going to summarize the form. I'm going to tell you how to choose U and dv and so on. Turn off your microphone, please. So we choose U to be, if the integral is in that form, I'm going to summarize the general form very shortly. Okay. Always choose U to be natural log of x. Okay. And then dv, you're going to see how it works. Actually, in many questions, you do not have to choose U and dv correctly the first time. If your choice doesn't work, you can always change, right? We choose dv to be x squared and then times dx. Okay. If I'm telling you how to choose U and dv, probably you can figure out the rest. And then we compute du. Du is you take the derivative of natural log of x, which is 1 over x. For the people who took the course a long time ago, you check the formula sheet. I told you to take a picture. The derivative of natural log of x is 1 over x. So do not forget dx, part of the differential notation. And then v, for v, we need a particular antiderivative of x squared. Anybody want to tell me v? V, please. what function has the derivative of x squared? It's 1/3. You take the derivative of what function you have x squared? I think you have 1/3 of x cubed. Right? We have seen this over and over again. Again, here you just need one particular antiderivative. Okay. And then we are going to use the by parts formula to get the integral. The rest should be simple. All the rest should be super simple. So the given integral, you treat that as u dv. Okay. Now we are using the by parts formula. You do not have to write u and v on this line. Okay. It's u times v. U times v is 1/3 of x cubed, and then times natural log of x. That's uv, u times v. Okay. And then minus v du. Minus v du. V is 1/3 of x cubed. Du is 1 over x, and dx. You copy everything from here. 1/3 x cubed, natural log of x, and then minus. Simplify this part. Okay. You can cancel out a factor of x. Minus 1/3. I think you have x squared. Right. X cubed here, x on denominator. You cancel out a factor of x. You have x squared dx. You're almost done. We're almost done. Okay. I think the final answer is 1/3 of x cubed, and then times natural log of x, minus antiderivative of x squared again is 1/3 of x cubed. So the whole thing is 1 over 9. 1/3 times 1/3, you have 1 over 9, right? X cubed. After getting rid of the integration notation, you plus. So you have the final answer. Simple enough. I think we summarized four forms. Now I'm going to add one more form. One more form of the integrals for which you can use the by parts formula. Okay. After I summarize this, you do another in-class quiz question. I think that's number 5. Again, we are trying to classify the integrals for which we can use the by parts formula. So later on, we are going to summarize many other forms of the integrals for different techniques. Okay. So this form is x to any power. So maybe x to the power of m. M can be any power, actually. Okay. M is not necessarily an integer, a whole number. M actually can be any real number. I think I was trying to use k to denote any real number. I'm going to use k here. Okay. It's x to the power of k, and then times natural log of x. K can be any number, so by that I mean this part can be a radical function even, right? For this form, you can use the by parts formula. Okay. When using the by parts formula, choose u to be natural log of x, and choose dv to be x to the power of k, and then times dx. I was trying to write k in here. It's good enough. In almost all the cases, it will work. That's another form we can use the by parts formula. Question number 8 is going to be a in-class quiz question. Okay. In-class quiz. The integral is essentially in the same form as what I told you, right? I will tell you how to choose U and dv, so maybe I will give you a few more steps before you finish. Okay. This function is essentially a power function. It's the function x to the power of 1/2. So maybe I'm going to rewrite the integral in a different form. So the integral of square root of x is x to the power of 1/2. I just did a conversion of that. The natural log of x and then dx here, right? We convert the radical function to the form of a power function. You see that's a particular case that the k value is 1/2. So we let x be, we let u be natural log of x. So don't be confused. And then dv is of course x to the power of 1/2 and then dx. And then to use the by parts formula, you need to get du and v. Okay. So du is equal to the derivative of natural log of x is 1 over x, 1 over x, then times dx. And then v is, anybody want to write down how to get v? So what is v? V is supposed to be antiderivative of x to the power of 1/2, which is a power function. To get antiderivative of a power function, you can use the power rule, right? So here you should have x to the power of this number plus 1, x to the power of n plus 1, n is 1/2. I think you have 3 over. I think Tyler got it right. We're trying to get antiderivative of x to the power of 1/2. And the formula I was trying to say is antiderivative of x to the power of n. We're trying to use that formula. Okay, is equal to, you know what formula I'm talking about, x to the power of n plus 1 over n plus 1, right? And then plus c. I was trying to say antiderivative of x to the power of 1/2 is 1/2 plus 1 in here, exponent, and then you invert numerator and the denominator here, right? We got du and v. Now we're ready to use the by parts formula. I will stop here, and then you'll figure out the rest, please. Okay. I will give you a little time. I will wait until somebody read the answer in the box. After you are done, you can write your answer in the chat, so we can compare the answers. uv minus vdu, vdu And probably you know how to cancel out this. You cancel out x from the numerator and the denominator. I was trying to tell you x to the power of 3 over 2 and then times 1 over x. So this thing is equal to x to the power of, I think, 1/2. Is that right? I think Karen got it right. I think it's right. Okay, you just keep on going to get the final answer. And then that's one of the in-class quiz questions. Good. The next question we're going to do is not on the handout. It's kind of on the handout, but not quite. I will show you what I mean. Okay. I'm going to do this. Okay. We're going to evaluate the integral of natural log of x. Get the integral of natural log of x. Okay. My principle, I told you, is not very universal. So this is the case. The integrand does not have two factors, right? It's not the product of two functions, but you can always imagine one as one of the two factors. So the my principle, when to use the by parts formula, still applies. You have only one way to choose u, I guess, right? And then dv should be dx. All the rest of the function should be dx. I realize many people could be confused about simple things. So du is equal to, we have seen that too many times, 1 over x and dx. Anybody want to tell me v? What is v? Which function has the differential of dx? So write it down, please. Write it down, please. Write it on the chat. What's v? It's x. It's nothing but x. Right? The derivative of x is 1. You just imagine there's a factor of 1 in here. And then we're going to use the by parts formula. You're going to see what's going on. Okay. Now the by parts formula, the given integral natural log of x dx in here. We figure out u and v and so on. Okay, u times v is x times natural log of x, and then minus v du, the integral of v du, the integral of x, and then du is 1 over x and then times dx. Right. Inside the integrand in here, essentially you have 1. X and x is cancelled. I'm going to write a new line. X times log of x minus the integrand now is 1. Actually, you do not have to write that 1. You just imagine there's a 1 in here. That's a permissible notation. If you actually, that's a better notation than writing 1. So do not ask me why. It's a convention, only a convention. Okay, now the final answer. X times natural log of x minus integrand is 1. We are thinking you need to think which function has the derivative 1. Which function? X, right? After getting rid of the integration notation, you plus c. That is the complete solution to the question I just made. It's an indefinite integral. Okay. Actually, all the questions we have done are indefinite integrals. Actually, there's a formula for there's a by parts formula. There's an integration by parts formula for the definite integral. That's the next thing we're going to do. Okay, it's not hard. It's not complicated at all. Okay. I'm going to write the title. Okay. It's called integration by parts. I was trying to write it by parts for definite integrals. It's on the course manual. It's in the course manual. It's in the textbook. But I will give you the formula. We assume all the functions are differentiable. Okay. So by that we mean we can talk about the derivative of any function. Actually, the rigorous condition is the derivative is continuous, so that we can talk about the integral. But the conditions are satisfied in many cases, in almost all the cases for the functions we talk about. So I'm not going to write the conditions. Okay. The integration by parts for definite integrals. Okay. The definite integrals, you have a lower limit, you have an upper limit. So now let's say you have the form of u dv. U and v are functions of x, a and b are values of x. Okay. So maybe I'm going to write something simpler here. Okay. Maybe u and v are, even I say differentiable, it's not too strict. Are functions of x with continuous derivatives. I told you in most cases the conditions are satisfied. Okay. And then the most important thing is to remember the formula for the by parts formula for definite integrals. It's very similar actually. Okay. U times v, and then you write a bar in here. You know the meaning of the notation. This notation is a symbolic notation. It means you need to compute the difference between two values of u times v. You write b in here, you write a in here. Again, that's a bar, that's a vertical bar. Minus the integral of from a to b, the integral of v du. That formula is called the integration by parts formula for the definite integral. Okay. We'll use that to do this question. We did the corresponding indefinite integral, right? So the way to choose u and v is the same. So we set u to be natural log of x, and then v is dx. The way to choose u and v is the same as we did. You still need to compute du and v. Du is 1 over x, and then times dx. Do not forget dx. And the v is equal to v is equal to x, you said, right? Now we are going to use the integration by parts formula for the definite integral. You see, I'm trying to copy and paste whenever possible. I'm trying to say I'm lazy. Actually, I'm trying to tell you whatever I write on the screen is essential. Do not omit more things than I did. Okay. Now you look at the formula here. Okay. The formula is here is still u times v. You just get the difference between two values of uv. So here is the corresponding definite integral for v du. U times v. Here you have x times natural log of x. It's because the integral, it's because the function is kind of long. Instead of using bar, I'm going to use square brackets to mean the same thing. You still compute the difference between two values of the function. You have e in here, you have 1 in here, okay? And then minus from 1 to e, the integral of v du. V is x. du is 1 over x, right? Again, I was using square brackets to replace the bar because the antiderivative is a little bit long. Okay, now we just plug in the numbers and eventually we get the value. The value, now let's recall the answer to a definite integral is a number. We're going to get the number by plugging in the numbers. Okay. I mean by plugging in the upper limit of v and the lower limit of 1. I'm going to do this one a little bit slower. Okay. How about I still keep that notation. Okay, x times natural log of x. You have 1 in here minus. I'm going to evaluate the integral first. Integrand is essentially 1. Antiderivative of 1 is equal to x. We have seen that earlier. Okay. So here you probably want to use a bar because the antiderivative is actually one function, has one term. You write e in here, you write 1 in here. Okay. Now we're going to get the answer. From here we're going to get the answer. Okay. You plug e into the function. You plug e into the function. You have e times, you replace x with e. Okay. Natural log of e. For a value like that, you have to get a number. I mean, in next step you have to replace natural log of e with 1. Okay. Natural log of e is equal to 1. And then you plug in 1, you have 1 times value is 1. Okay, you have 1 times of 1. I know natural log of 1 is equal to 0. I'm trying to show you how to plug numbers. Okay. And then the whole thing in here, I will put the meaning in brackets. You plug e, I believe you have e minus 1 in here. Right. Okay, natural log of e is equal to 1, I told you earlier, and the natural log of 1 is 0. You really do need to know these values. So this part essentially you just have a e, okay. You have 1? You have 1. That's different from what I remember. You have 1. The final answer is 1. Anybody see I did something wrong? I think 1 is right, probably. 1 is right. Okay. That's a question designed to show you the substitution rule for definite integrals. Any questions about this? On the assignment, you are going to have a question regarding the substitution rule for the definite integrals. Okay. I hope this one is not too hard. After we do question 9 and question 10, I think we have enough questions to do some more questions. We'll move on to question 9. I just changed my mind. I want to do 10. And then you do 9 later, okay? From 10, probably you can see the general form. So later on, I'm going to give you one other form of the integral. One other class of the integral for which you can use the by parts formula. Now, take your best guess. How do you choose u and dv, please? How to choose u and dv? You don't want the antiderivative to be too hard to get. This may not be work. This may not choosing u to be x may not be working. So because so later on you need to get antiderivative of the other factor. We do not know the antiderivative of inverse tan of x, but it's easy to get the derivative of inverse tan, right? So we choose u to be inverse tan of x, and then we choose and then v. You have no other choices. V, it has to be x times dx, right? Here. And then we compute du antiderivative of inverse tan. Look at your formula sheet. It's on your formula sheet at the very beginning of the class. I told you to take a picture. The derivative of inverse tan of x is 1 over 1 plus x squared. You could write dx on the numerator, or you can write dx here. Either way is okay. And then v, we need to compute v, right? V, we need antiderivative of x. You think which function has the derivative of x? I believe it's half of x squared. You could think about the power rule. Here, I want to repeat, you just need one particular antiderivative. Any function has many antiderivatives. They differ by a constant. So here you just need one particular antiderivative. Okay, and then we follow the by parts formula, the given integral of that. Using the by parts formula, so this term is u times v. So 1/2 times x squared times inverse tan of x, u times v. Okay, and then minus v du, minus v is half of x squared du. Where's du? Du is here. Okay, write the whole thing is something like this. 1 plus x squared here. I was trying to write v du, the integral of v du, v is half of x squared, so which is half of x squared here. Du is 1 over 1 plus x squared, and then times dx. The integral we are going to evaluate is essentially the integral of a rational function, in which we are going to have a whole section to talk about the integral of a rational function. By rational function, we mean the quotient of two polynomials. Okay. At this point, I'm going to tell you the trick. I'm going to use a tricky method. But if you do not understand the tricky method, so don't worry. Later on, we are going to have a whole section talking about how to evaluate the integrals of a rational function. For this one, for the integral of, I just evaluate the integrals separately, and then you can plug it back. Okay. I did not include 1/2 in here. Okay. Again, I hope it's not too tricky, but later on you'll see the general method. Okay. I'm going to do it. I will try to let you follow me. Okay. So here I'm going to add 1 and then minus 1. So basically, for adding or subtracting fractions, I'm doing it backward. I want to write this term as, I will give you the next step. Again, so don't worry if you cannot follow me here. Later on, we are going to have a section to integrate rational functions. If you do not know what's going on, you subtract the two fractions. We can go back to that. That's how it works. I just did the other way around. Okay, now at this point we can evaluate the integral now. Okay, antiderivative of 1 is equal to x. Antiderivative of 1 over 1 plus x squared is equal to arctan, or inverse tan, using our notation. Inverse tan of x and then plus c. Can I stop here?